BSc Chemistry Terpenes. This is the second lecturer series of terpenes presented by Dr. Giridhar M., Assistant Professor of Chemistry, Department of Collegiate Education. Contents: isolation of mono and sesquiterpenoids. So in that we will be studying steam distillation, solvent extraction, structural elucidation of citral, synthesis of citral, structure of menthol, structure of camphor, and structure of alpha terpenol. Let us move to isolation of mono and sesquiterpenoids. Both mono and sesquiterpenoids have common source, that is essential oil. Their isolation is carried out in two steps. So one is isolation can be carried out from essential oils from plant parts. Okay, and second one is separation of terpenoids from essential oils. So these are the two methods. One is from plant parts and one is directly from essential oils. So there are four methods of extraction of oils. One is expression method, steam distillation, extraction by means of volatile solvents, adsorption in purified fat. In this we have to study steam distillation and extraction by means of volatile solvent. So let us move to steam distillation. So steam distillation is most widely used method. In this method macerated plant. So illi macerated andre the plant material is brought, it is grinded into fine powder, or in water it is grinded in water to give macerated plant material, which is steam distilled. Okay, with water when steam distilled. So now what happens, whatever will evaporate, along with this our terpenes will also evaporate and it passes through this condenser and finally it condenses and drops here, collects here as liquid. And these terpenoids, they are oils, they are not miscible with water and hence they can be separated by using solvent extraction funnel. Okay, by using solvent extraction funnel we can separate both this oil and liquid. If our terpenoid which we have to extract will undergo decomposition at high temperature, then here it is extracted with, initially the plant material is filtered, the clear liquid is extracted with petrol at 50 degrees centigrade to obtain terpenoids. Okay, after evaporation of petrol we get terpenoid. So this is steam distillation method. So plant material is macerated and then filtered to remove plant material and then it is distilled to get terpene as well as water, which can be separated by using solvent extraction funnel. Extraction by means of volatile solvent. Solvent extraction is done by submerging plant material in solvent. So usually the solvents used are methanol, hexane, ethanol. So here plant material is submerged in solvents like methanol, ethanol, hexane. So and the terpenes are extracted into the solvent after soaking for some time, maybe 1 day or 2 days. Then plant material is removed and solvent is evaporated, leaving behind terpenes. So this is by using volatile solvents. So different solvents can be used and selection of solvent depends upon the type of terpene we have to extract. For example, the method which we use for gamma terpene cannot be used for para-cymene. So for each terpene to be extracted, different method has to be developed. Structural elucidation of citral. So here initially molecular formula of citral is determined to be C10H16O by elemental analysis. So elemental analysis is a technique which gives the amount of carbon, hydrogen and oxygen present in the sample, and from that we can propose a molecular formula of that compound. So from elemental analysis, it is found to be C10H16O for citral. So now we know that these terpenes contain unsaturated. These terpenes are unsaturated, that is, they contain double bond. So first we have to confirm the presence of double bond. So when the citral or sample is treated with bromine, we get tetrabromocitral, and we observe that for 1 mole of citral, 2 moles of bromine is consumed. So thereby we confirm that there are 2 double bonds in citral. So next is to find the position of this double bond. So the position can be found by treating citral with KMnO4. KMnO4 is very strong oxidizing agent, and it will break this double bond to give acetone. So this is the acetone. Okay, when it breaks here, it gives acetone, and then when it breaks here and here, it gives levulinic acid, and finally breaking here, it will give oxalic acid. Similarly, ozonolysis gives acetone, levulaldehyde and glyoxal. So difference between ozone and KMnO4 is very strong oxidizing agent, therefore it gives acid here, whereas ozone gives aldehyde. So here also in case of KMnO4 it is oxalic acid, whereas in case of ozone it is dialdehyde, that is glyoxal. So from the above product show that citral is a acyclic compound containing 2 double bond. Okay, it contains 2 double bond, and the position of double bond is confirmed with KMnO4 and ozonolysis. Now the corresponding saturated hydrocarbon of citral, that is, if double bonds are not there, okay, here double bonds are not there, and if it is completely saturated, then its molecular formula would have been C10H22. But we have molecular formula which is C10H16O. This shows that citral contains 2 double bond. Okay, in citral we see that there is 2 double bond. And when KHSO4, okay, citral is treated with potassium hydrogen sulfate, so we see that citral we get parakymine. Okay, we get parakymine, which is cyclic compound, and hence formation of parakymine and product obtained from ozonolysis reveal that citral is formed by joining of 2 isoprene units in head to tail fashion. Okay, it is we confirm that citral is open chain. Citral is having open chain structure, and it is formed by connection of 2 isoprene units by head to tail fashion. So on the basis of above fact, structure of citral is proposed as, so this is the skeleton structure of citral, this is parakymine, and this is the proposed structure of citral. And finally, citral on binding with aqueous potassium carbonate yielded 6-methyl 5-ene-2-one, okay, and acetaldehyde. So the formation of this can only be explained on the basis of proposed structure. So therefore this is the structure of citral. So now in modern techniques, NMR, IR, mass spectroscopy is used to confirm the structure of citral. But during those days, when citral structure was confirmed, it is only by chemical methods, so which we have discussed right now. Okay, that is the structural elucidation of citral. Synthesis of citral. Citral is synthesized by using Barbier-Boult-Tymans synthesis. So in this method, methyl heptanone is converted to guaranic ester by using Reformatsky reaction, Guaranic ester is then converted to citral by distilling a mixture of calcium salts of guaranic acid and formic acids. So here methyl heptanone. So this is methyl and 1, 2, 3, 4, 5, 6, 7. Methyl heptanone. So when this is treated with zinc, ethyl iodoacetate and H+, which is Reformatsky reaction. So we get a product this undergoes dehydration, it loses water and forms a double bond here. This is guaranic ester. So this guaranic ester, when treated with calcium salt, hydrolysis will take place and followed by dehydration to give citral. So this is the synthesis of citral. Reformatsky reaction followed by dehydration followed by hydrolysis and dehydration to get citral. Menthol. Structure of menthol. Menthol is organic compound made synthetically or obtained from peppermint or other mint oils. So this is obtained from peppermint or other mint oil. So it is waxy crystalline solid, white in color, and it melts, our melting point is between 41 to 43 degrees centigrade. So menthol has local anesthetic, counter irritant qualities. It is widely used to relieve minor throat irritation. So andre cough syrups alli menthol use ಮಾಡ್ತಾರೆ. In cough syrup menthol is also used. So menthol also acts as weak kappa opioid receptor agonist. So the main form occurring in nature is minus menthol. So that is levorotatory. Levorotatory andre when plane polarized light is passed through menthol, it will rotate the plane of that polarized light towards left side. So hence it is levorotatory. So which is assigned 1R, 3R, 4S configuration. So this is R and S configuration assigned, and it is 1R, 3R, 4S configuration. So this is the structure of menthol. So this is naturally occurring menthol, which is 1R, 3R, 4S menthol. This is R and S, 3 stereo centers. Whereas this is its enantiomer, that is 1S, 3S, 4R, which will be plus menthol. Now the molecule can exist as a pair of optical isomer, obviously. So and menthol has 3 asymmetric carbon, as already told, asymmetric carbon, the 1, 2, 3. So here asymmetric carbon means carbon attached to 4 different groups. So here we can observe that this carbon is attached to hydrogen, methyl group, one group, and this whole thing another group, and this is another group, 4 different groups. Similarly this carbon, one hydrogen, OH, and this group and this group. So three isomers are there, and we know that when 3 stereocenters are there, it can form 2 to the power of n, that is 2 to the power of 3, 8 isomers, and the structure of 8 isomers is given. This is 1, this is 6 isomers are given, structure of 6 isomers. In total it can form 8 isomers, and this is the cyclic chair form of menthol, and this is the most stable form because here all the groups are present in equatorial position. Hence this is the chair form minus naturally occurring levorotatory menthol, all the groups present in equatorial position. So this is the structure of menthol. So next is camphor. So camphor is also known as Cinnamomum camphora because it is obtained from cinnamon tree. So it's a terpene that is commonly used in creams, ointments, lotions. Camphor oil is the oil extracted from wood camphor trees and processed by steam distillation. It can be used topically to relieve pain, irritation, and itching. So this is the structure of camphor. So once again here 2 stereocenters are there, and owing to 2 stereocenters, 2 to the power of n, it can form 4 isomers. Okay, 4 isomers. If this is R, okay, this will be S. Okay, similarly this can be R, S, R, S. So such type of 4 isomers are possible. So next is alpha terpenol. Terpenol is a monoterpene alcohol. Monoterpenol means two isoprene units joined in head to tail fashion. Okay, so you can see here, this is one unit and this is another unit. So isolated from variety of sources such as cashew nut oil, pine oil, petit grain oil. So there are 4 isomers. So alpha, beta, gamma terpenol and 4 terpenol. So these are the 4 isomers of this terpenol. So the structures are given. Okay, this is alpha terpenol. Only thing is here, the position of double bond and OH will vary. So this is alpha terpenol, this is beta terpenol, this is gamma terpenol, and this is 4 terpenol. So terpenol has pleasant odor and pleasant odor similar to lilac. Okay, lilac is a compound and this terpenol has pleasant odor, and it is used as common ingredient in perfumes, cosmetic and flavors. So flavors are substances which are used to add to food ingredients to give sweet flavor. So this is the structure of, okay, terpenol. And we observe that terpenol is usually a mixture of these isomers, and in this alpha terpenol is the major constituent. So you can observe here, alpha terpenol is monoterpenide with 2 isoprene units. It is further classified as monocyclic, that is contains 1 ring terpenoid, monocyclic terpenoid. And you can see here the green shows one isoprene unit and blue is another isoprene unit, and these 2 isoprene units are joined in head to tail fashion. So this is about terpenol. So these are the references. Thank you.